Today again in this topic, what you call Gauss theorem, we are going to learn some new things, that is applications of Gauss theorem. Yesterday we studied many things in this topic, namely surface vector. You know what is surface vector? You know what is called electric flux. Do you remember the definition of electric flux? I will speak once again. So electric flux is the total number of lines of force penetrating through an area along the normal. Along the normal means in the direction of the surface vector. Then we studied yesterday Gauss theorem. According to Gauss theorem, the total electric flux through an area, through a closed surface area, is equal to 1 by epsilon 0 times the charge enclosed by it. The same definition can also be said as the surface integral of the electric field over a closed surface is equal to 1 by epsilon 0 times the charge enclosed by it. Remember once again. So at this hour, I am going to explain you the applications of Gauss theorem. Gauss theorem can be applied or can be used to find the intensity of electric field due to charged bodies at a certain distance away from those. The first application I am going to choose is a line of charge. This is a line of length L and it is a charged line. It is uniformly charged, having a linear charge density lambda. Linear charge density lambda means if Q is the total amount of charge present in the line and L is the length of the line, then linear charge density lambda is equal to Q by L. What is that? Lambda is equal to Q by L, or Q is equal to lambda into L. So this is the line shown here. So any charged body can produce an electric field around it. Suppose there is a point P at a perpendicular distance r away from the line of charge, and these arrow-headed lines are showing the electric field lines. So electric field lines. So these electric field lines are passing through the curved surfaces. So flux will remain only, am I correct? So these are field lines. We have to find the intensity of electric field at the point P due to this charged line of charge. We have to use what? Gauss theorem. For Gauss theorem to be used, one thing is very, very necessary. What is that? There must be a closed surface. In this case, the closed surface I am taking is a cylinder enclosing this charged body. Right? We can use any shaped body, but that shaped body must be closed, that's all. Shape is not a criteria. Any shape there can be. It is not necessary that this must be cylindrical only. Here I am taking cylindrical Gaussian surface because that is very similar to, that means that cylindrical surface is fit for this line of charge. That is what cylinder is taken. There can be any shaped closed surface that must enclose the charge. So here I am taking cylinder as the Gaussian surface. So on the Gaussian surface there is a point P at a distance r. We have to find the intensity at this point at a distance r from the charged body. What distance? Perpendicular distance. And where this small area is lying on the Gaussian surface. So we are considering a cylindrical surface that is enclosing the linear charged body, and such that the point P is lying on the surface of the Gaussian surface or Gaussian cylinder, where we wish to calculate the intensity of electric field due to this line of charge. So here you will see one more thing. This is the line of force. Already I said line of force is denoted by arrow-headed line. Here these two arrowheads are showing that one is for intensity of electric field, other is for the surface vector. That means we are placing a small area at the point P. Small area means ds area is considered. ds area has a surface vector. In this case, you see that surface vector and the intensity of electric field both are the same direction. Therefore, the angle between E and ds is equal to 0. Now we will first calculate the small electric flux through this small area. What is the magnitude of the area? ds. Everybody knows that yesterday we have already explained the general expression for electric flux through a small area d phi is equal to E dot ds, vector E dot vector ds. That's equal to E ds cos theta. In this case, as theta is equal to 0, the small flux through this small area ds is equal to simply E ds. Right? One more thing you have to remember. The flux is only through the curved surface only. This bottom and upper surface, there is no flux. That also you must keep in the mind. Why it is so? See, I explained that also. If you construct a field line like this, the field lines in the arrow will go like this, and the surface vector, if you take a small surface here, surface vector is like this. The surface vector ds and E will be 90 degree for both the top and bottom surfaces. Therefore, the flux through the bottom and upper surfaces, that will be is equal to 0. No flux will be there. Flux will remain only through the curved surface of this Gaussian cylinder. Yeah. So now coming back, the small flux of this small area ds is given by d phi is equal to vector E dot ds. Everybody knows that, already said many times, that is equal to E ds cos theta. That is equal to simply E ds, because in this case theta is equal to 0. You see that because ds and E are parallel to each other. Therefore, theta is equal to 0. What is vector ds? Surface vector. Surface vector and the intensity of field vector both are acting along the same straight line. They are parallel. Therefore, theta is equal to 0. So, through a small surface area on the Gaussian surface, if the small flux is d phi is equal to this value, then what will be the total value of electric flux through the entire curved surface? Only curved surface, remember. Why that? Through the upper and lower surface, there is no flux. Flux will remain only through the curved surface of the Gaussian surface. Okay, that is given by the total flux through the entire curved surface of the Gaussian cylinder is given by phi E. That was d phi E, this is phi. Phi means total flux. Total flux is equal to surface integral of the electric flux. Surface integral electric flux means surface integral E dot ds. That is equal to E dot surface integral ds. That is equal. Integral ds is equal. What is integral ds? Integral ds is the surface area of the curved surface of the cylinder. The curved surface area of a cylinder is equal to 2 pi RL. What is 2 pi RL? The circumference of the base into length of the cylinder. That is 2 pi RL. This is equation number 1. But by Gauss theorem, everybody knows that Gauss theorem. What is Gauss theorem? According to Gauss theorem, surface integral of the electric field. Surface electric field means total electric flux. What is it? Surface of the electric field is also called as total flux. That is total flux. Total flux phi is equal to Q by epsilon 0. This is equation number 1. This is equation number 2. So, relating these two equations, we can write E into 2 pi RL is equal to Q by epsilon 0. That is E is equal to Q by 2 pi RL into epsilon 0. But Q is equal to lambda L. Hence, E is equal to lambda L divided by 2 pi R epsilon 0. So, finally, we can write the intensity of electric field at a point P, distant R. What distance? Perpendicular distance R from the line of charge. E is equal to 1 by 2 pi epsilon 0 into lambda by R Nc raised to minus 1. Nc raised to minus 1 is very famous in the world. Newton per coulomb. Or in terms of instead of Newton per coulomb, we can write volt per meter also. So this is an application we have explained here. Today we have explained the Intensity of electric field, how found? Using Gauss theorem. First application is line of charge. Line of charge at a distance r away from which what is the intensity of electric field. This is the first application of Gauss theorem. The further topics will be taught tomorrow. Thank you.